air you're sitting on, the air you breathe. What if that's just like one layer? And as you zoom way in, I mean really, really close, the rules just completely change. The universe gets, well, stranger. Probabilistic even, maybe? Made of tiny vibrating strings.
Yeah, it's exactly the wild ride we're taking today. We're diving deep into the different scales of reality physics tells us about.
Right.
Exploring how our whole understanding shifts, sometimes quite radically, as we go from, say, the atomic level down to these theoretical realms we can barely even picture.
And this whole exploration, this deep dive, it's happening because you sent us this amazing stack of sources, articles, notes, all about this incredible journey into the infinitesimally small.
Yeah, great stuff to work with.
So our mission today, okay, let's unpack this. We want to go through these sources, really get a handle on the key theories running the show at these different scales, and see how the very idea of reality gets, well, redefined.
It really does. Physics gives us this layered view of the universe. It's almost like peeling an onion, isn't it?
Yeah, exactly.
Each layer reveals a different set of rules, different characters, you could say. And the theories we use, they completely depend on the scale we're looking at, the energy involved.
Right, like Newton works for baseballs, but you need Einstein for black holes or GPS satellites, that kind of thing.
Precisely.
But going down in scale, the changes seem even more fundamental. It really feels like the fabric of reality itself is just different depending on your zoom level.
Absolutely. The concepts change, the particles, the forces, they all transform as we probe smaller and smaller distances. It's a whole different world down there.
So where do we start this descent? Where do things first get weird?
Well, the first big jump away from our everyday intuition happens in the realm of atoms and molecules. That's the domain of quantum mechanics.
Ah, quantum mechanics, famous for being counterintuitive. What kind of scales are we talking about here, size-wise?
So we're looking at nanometers, which is a billionth of a meter. Think 10 meters, that's where you find molecules.
Okay.
And then down to femtometers, that's a millionth of a billionth of a meter, or 10 nanometer. That's the scale of the atomic nucleus itself.
Wow, okay. Incredibly tiny already, but I guess still huge compared to where some theories want to take us later.
Oh, definitely. We've got a long way down to go.
And you said classical intuition fails here. So how is reality different at this quantum scale?
Well, forget solid little balls bouncing around predictably. The sources describe it really well, actually, as a fuzzy, probabilistic landscape.
Fuzzy and probabilistic, okay.
Particles aren't just particles, they also act like waves. That's the famous wave-particle duality.
Right.
And their properties, like where they are, how fast they're moving, they aren't actually definite until you measure them. They can exist in multiple states at once, superposition.
So it's not just that we don't know where it is, it's that it literally doesn't have a single place until we look.
Yeah.
That messes with your head.
It absolutely does. Reality itself has this uncertainty baked in. It's not just about our limitations in measuring it. It's fundamental.
And is there like a key number or constant that defines this realm? What makes it quantum?
There is. It's Planck's constant, usually written as h. It's this fundamental number that basically dictates the minimum size of energy packets, or quanta. It tells you when quantum effects kick in, and classical physics just won't cut it anymore.
I got it. Planck's constant, h, and the forces. What's holding atoms and molecules together at this scale?
Primarily electromagnetism. That's the force mediated by photons, particles of light.
Ah, okay.
It's what binds electrons to the nucleus to make atoms, and then binds atoms together to make molecules. It's absolutely essential for, well, all of chemistry and pretty much everything we see around us.
Okay, so quantum mechanics handles the fuzzy, probabilistic world of atoms and molecules. But you said the nucleus is at the femtometer scale. If we try to look inside the nucleus, or even smaller.
Then we need to go deeper still. That takes us below the scale of the nucleus, into the realm of what we currently believe are the truly fundamental particles.
Yeah.
And that world is described by the standard model of particle physics.
The standard model, okay. How much smaller are we talking now? What's the scale here?
We're jumping down quite a bit further. Think atometers, which is 10 eurometers, down to maybe zeptometers, 10 eurometers.
Okay, at out on femtometer, these prefixes are getting intense. How does that compare to the nucleus?
Well, remember, a femtometer of the nucleus size is 10 euro. So we're talking 1,000 to 1,000,000 times smaller than the nucleus itself. It's a huge leap inwards.
And how on earth do physicists actually see things that small? You can't just build a microscope, can you?
No, definitely not. This is where particle accelerators come in. Machines like the Large Hadron Collider, the LHC over at CERN.
The big one in Switzerland.
That's the one. They smash particles together at incredibly high energies, close to the speed of light. These collisions create conditions just for a fraction of a second where these tiny scales become accessible. It's like using energy as your microscope, probing distances down to that 10, even 10 arc meter range.
So the LHC is our window into this atometer world. What does the standard model tell us we find there?
We find what one of the sources called a menagerie of elementary particles. We're not talking about protons and neutrons anymore. Those are composites.
Ah, right. They're made of smaller things.
Exactly. We're talking about their building blocks. Quarks and leptons, things like electrons or leptons. Quarks make up protons and neutrons. These are, as far as we know, fundamental.
And the standard model also covers forces, right? Which ones?
It covers 3 of the 4 known fundamental forces. Electromagnetism, which we already mentioned. Then there's the weak nuclear force, which is responsible for certain types of radioactive decay. And the strong nuclear force, which is what glues quarks together inside protons and neutrons, and also holds the nucleus itself together against the electromagnetic repulsion of the protons.
Okay, so strong, weak, and electromagnetic, but not gravity.
Not gravity. That's one of the big limitations of the standard model. It works incredibly well for the other 3, but gravity just doesn't fit in the same framework.
Interesting. And what are these particles like, the quarks and leptons, at the standard model scale? Are they fuzzy like in quantum mechanics?
Well, quantum mechanics still applies, but according to the standard model and all our experiments so far, these particles appear to be truly point-like.
Point-like, meaning no size at all, no internal structure.
As far as we can tell, down to the scales the LHC can probe, yes. They seem to have no measurable size or anything inside them, just points with properties like mass and charge. And the interactions between them are super energetic.
Okay, so quantum mechanics for the atomic fuzziness, the standard model for these point-like fundamental particles and 3 forces. But you mentioned gravity is missing, and the sources definitely hint at theories trying to go even deeper, right? To maybe fix that.
Absolutely. That's where theoretical physics really pushes the boundaries. To try and bring gravity into the fold and answer other deep questions the standard model doesn't address, physicists explore ideas that operate at scales far, far smaller still. And the most famous of these is probably string theory.
String theory. Okay, now we're getting into seriously theoretical, maybe even speculative territory, yeah. What kind of scale are we talking about for strings?
We are making an absolutely enormous jump down. We're heading towards the Planck length.
The Planck length. What is that number again?
It's about 10 nanometers.
Okay, hold on. 10 to the minus 35. That's, I mean, the standard model was down at 10 years. So this is like, what, 17 orders of magnitude smaller. That number is just, it's hard to even conceive of.
It is profoundly small, almost impossible to grasp intuitively. But one of the sources had a brilliant analogy that helps a little.
Oh, yeah. Lay it on me.
Okay, imagine you could somehow blow up a single atom to be as big as our entire solar system.
Whoa, okay. Solar system-sized atom.
Right. Now, on that scale, one of these theoretical strings would only be about the size of a tree.
A tree inside a solar system-sized atom. Okay, wow, that really puts it in perspective. That's
Yeah,
that's unbelievably tiny. Smaller to a proton than a proton is to us, basically.
way smaller, yeah. So at this almost infinitely small level, what's the big idea? What replaces the point particles of the standard model?
The core idea of string theory is that those fundamental particles, the quarks, the electrons, the photons, all of them aren't actually zero-dimensional points.
Okay.
If you could zoom into the Planck length, you'd see they're actually tiny, one-dimensional vibrating filaments, like incredibly small loops or segments of string made of pure energy, vibrating filaments like tiny guitar strings.
Kind of, yeah. That's a common analogy. And just like a guitar string can vibrate in different ways to produce different musical notes.
Ah, I see where this is going.
These fundamental strings can vibrate in different patterns, different modes. And these different vibrational modes are what we perceive as different particles with different properties: mass, charge, spin.
So an electron is one vibration pattern, a quark is another, a photon yet another, all just different notes played on these fundamental strings.
That's the idea. It's a way to unify the particle zoo. They're all just manifestations of the same underlying object, the string.
And what's fascinating here is, does this help with gravity? You said the standard model couldn't handle it.
Yes, this is one of the biggest appeals of string theory. It turns out that among the possible vibrational modes of the string, one specific mode has exactly the properties predicted for the graviton.
The graviton. That's the hypothetical particle that carries the gravitational force, right?
Exactly. The particle equivalent of the photon for electromagnetism. String theory naturally predicts its existence just as another vibration of the string. So it offers a framework where gravity can be unified with the other forces described by the standard model, potentially.
That's huge, a possible path to a theory of everything. So, string theory. Planck length scale, vibrating strings instead of points, potential unification including gravity. But the sources also mention something called M theory. Is that different or related?
It's closely related, emerging out of string theory research. As physicists explored string theory, they found there wasn't just one version, but 5 different consistent versions.
Oh, okay. That sounds complicated.
It was. But then, particularly through the work of Edward Witten and others in the mid-90s, it was realized that these 5 string theories might actually be different aspects, different limiting cases of a single, deeper, underlying theory.
And that underlying theory is M theory.
That's what we call it, yes, M theory. The M is famously ambiguous, could stand for membrane, magic, mystery, mother.
Huh, okay. So it's even more fundamental than string theory.
Potentially, yes. It's seen as a more encompassing framework, maybe the candidate for a theory of everything. It tries to unify all 5 superstring theories. And it operates in, get this, 11 dimensions.
11. Not the 4 we know. 3 space, 1 time.
Nope. 11 space-time dimensions, according to M theory. 10 of space and 1 of time.
Where are the other 7 spatial dimensions, then?
That's a great question. The idea is that they are compactified.
Compactified, meaning?
They're curled up incredibly tightly, probably on a scale close to the Planck length itself. So small that we can't detect them or move in them in our everyday experience, or even with our current experiments. Imagine looking at a garden hose from far away, it looks like a 1D line. But get close, and you see it has a second, curled-up circular dimension.
Ah, okay, so these extra dimensions are wrapped up, hidden from view because they're so tiny.
That's the prevailing idea, yes.
Yeah.
And M theory isn't just about strings either.
Oh, what else there?
It includes higher dimensional objects called branes, which is short for membranes.
Branes, like 2D surfaces?
They can be, yes. But also 3D volumes, or even higher dimensional objects, p-branes, where p denotes the number of spatial dimensions they have. So strings are 1 branes, a 2D membrane would be a 2 brane, and so on.
Okay, so M theory has strings and these brane things and extra dimensions. If we connect this to the bigger picture, what does that imply about our universe?
Well, one of the most mind-blowing implications is that our entire universe, the familiar 3 spatial dimensions plus time that we perceive, might actually be one of these branes.
Wait, what? Our whole universe is a 3 brane.
It's a possibility within the theory, yes. A 3-dimensional surface or volume existing within that higher dimensional 11-dimensional space, often called the bulk.
We could be, like, living on a sheet of paper floating inside a much larger, higher dimensional room we can't perceive.
That's one way to visualize it, yes. Our reality could be confined to this brane, while other dimensions, and possibly even other branes, other universes, exist out there in the bulk. That's a pretty staggering thought.
Staggering is an understatement. Okay, so let's recap this whole journey downwards. We started at the sort of nanometer down to femtometer scale.
Right. Atoms and molecules. Governed by quantum mechanics, that fuzzy, probabilistic world where particles are also waves and superposition happens. Electromagnetism is key there.
Then we zoomed way in past the nucleus to the atometer or zeptometer scale.
That's the standard model's turf. Point-like fundamental particles, quarks and leptons interacting via the strong, weak, and electromagnetic forces, probed by things like the LHC. Still quantum, but different descriptions.
And then we took that massive theoretical leap down to the Planck length, 10 nanometers.
Where string theory suggests those points become tiny vibrating strings, offering a way to potentially unify all particles and forces, including gravity, through their vibrations.
And finally, M theory emerges, hinting at an even deeper 11-dimensional reality, unifying string theories and introducing branes.
With the wild possibility that our entire universe is just one of these branes floating in a higher dimensional bulk.
Wow. It really feels like at each step, the description of reality gets, well, weirder, more abstract.
It certainly does. From wave functions to point particles to vibrating strings and hidden dimensions and branes, it moves further and further from our everyday intuition.
But also, maybe more unified, trying to connect everything together.
That's the ultimate goal, yes. Yeah. Theories like string theory and M theory are attempts to find that single underlying framework that explains everything. As the sources put it, each theory paints a picture on a finer canvas, showing us a cosmos that's far more intricate and bizarre than our ever-know experience would suggest.
It really hammers home that the solid, predictable world we live in is just the surface layer of something incredibly deep and strange.
It absolutely challenges our basic assumptions about what reality is. The universe, especially at these tiny scales, is just full of mystery and, frankly, mind-bending possibilities.
So for you listening right now, what does all this mean? Well, hopefully you've just navigated some really cutting-edge, complex ideas in physics pretty quickly.
Yeah, you've gotten a glimpse into how physicists are grappling with the fundamental nature of reality, from quantum weirdness all the way to speculative strings and brains.
It gives you, hopefully, a new appreciation for the sheer complexity and hidden layers packed into everything around us, even the most mundane object.
It's a reminder that there's likely still so much we don't understand about the fundamental workings of the cosmos.
We've definitely covered an amazing range of scales today. The quantum fuzziness, the point particles, the theoretical strings, the potential hidden dimensions of M theory. Quite the journey.
And again, this whole deep dive was fueled by the excellent sources you sent us, guiding us through these frontiers.
So let's end with this thought, building on that M theory idea. If our universe might really be just a three-brain floating in a higher dimensional space.
This raises an important question. How would that possibility, if true, fundamentally change your understanding of, well, everything, our place in the cosmos, the nature of space itself, maybe even the origin of the universe? Something to ponder.